So let's finish up with a quick summary of the things that we've covered in this lecture. The main topic has been the symbolic method for labeled classes, and particularly the transfer theorem, which shows how the constructions that we consider transfer to operations on generating functions. So we consider the disjoint union operation, and the main one, which is the labeled product operation, where we relabel objects in all possible ways, and we get a product on the generating function. Sequences of length k, which give a generating function a to z to the k, or sequence of any length, 1 over 1 minus. Same with sets of length k, or sets of any size, and cycles of length k, or cycles of any size. And there's many others that people have defined, like the box product, which has a corresponding operation on the generating function. With these basic operations, and just a few examples, there's many other examples in the book, we were able to define a whole host of combinatorial classes, all with relatively simple descriptions, and then leading to directly from the transfer theorem to exponential equations that exponential generating functions have to satisfy. And we have variations on these to lead to a huge variety of different combinatorial classes, and still, though, have specific equations that the generating functions have to satisfy. So that fits with our overview. To analyze properties of a large combinatorial structure, we use the symbolic method to get directly a generating function equation. Now, it's important to note that the equations that we get vary widely in nature. Some of them are quite simple, some of them are quite complicated, but those are the generating functions of the counting sequences that we seek. So in the second part, where we derive asymptotics from generating functions, we're also going to need general tools that can handle all of these different types of generating functions. But still, the derivations that give us the generating functions were all really essentially quite simple. In fact, to the point where, again, this brings in also unlabeled classes, we can automate the transfer from specifications to generating functions. And in fact, Philippe and his students, Bruno Salvi and Paul Zimmerman, did so in the 90s. And much of this work is reflected in modern symbol manipulation systems. Another thing we can do is use specs to generate huge random structures. One easy approach is to just take the spec and use a recursive program that is based on the spec. And that's okay, but it doesn't get you really large structures because it takes quadratic time. But there is a probabilistic method that gets, for a given size, that gets a random structure of approximately that size and works in linear time. And this is, becomes increasingly important for checking whether a combinatorial model that someone might have of the real world actually matches what's observed in the real world. You can generate a large number of random structures and check if their properties correspond to the real world object that's being studied, whether it be a DNA sequence or a computer network or whatever else is found that people are studying nowadays. So that's called Boltzmann sampling, and that's a reference for that as well. But I think, again, it's all about the utility of generating functions. And really, the bottom line is that without something like the symbolic method or generating functions, people were doing really horrendously detailed and difficult calculations. And this approach really does eliminate virtually all of them. That's a summary of the symbolic method, both for labeled and unlabeled objects.